Hi guys, I hope you're all doing well. So in this video, we're going to start talking about our next topic, which is a different type of shape that we'll be calculating the volume of. So far we've looked at volumes with known cross sections. This is a very different method from that. This is called volumes revolution, and there's two methods that we'll talk about. We're going to start with the simpler method first, which is the disk method, and we're going to just start at the X and Y axis today, and then tomorrow we'll kind of expand into a few other situations. Okay, let's dive in. Okay, so to recap area, because we will be calling back to that again with this volume method as well. So area between curves with respect to X and with respect to Y. So with respect to X, your upper and lower bounds are both in terms of X, right? You've got A and you've got B. And you just do the greater function minus the lesser function. And in terms of the graph, greater or lesser corresponds to top and bottom. Right, so the greater function will be on top. So if you have a picture of the graph, it's really easy to determine which one is greater, which one's lesser. And then your X boundaries will correspond to the X value on the left and the X value on the right. That might be the intersection of the two curves, or it might be specified for you on one or both sides. Now, if you're doing area with respect to Y, instead, you have to think sideways. And everything's in terms of Y, right? So that your boundaries, which we're calling C and D here, right? But those are Y values. That's really important to forget, to remember. Easy to forget. And you're still doing the greater function minus the lesser function, but you're thinking about it sideways, right? So instead of top minus bottom, if you're going with respect to Y, then that would be right minus left. So you just have to determine which curve is on the right and do that one minus the one on the left. Okay, so in volumes of revolution, the whole idea is that you're spinning something around. And what you're going to find is that these formulas all kind of come back to the idea of the volume of a cylinder. So if you have a cylinder, the whole idea of a cylinder is that you have some kind of circular base, right? And that you've got area of a circle is pi r squared. And that the idea is that you have some circular base and then you have a height coming up out of that. So the volume of a cylinder, you're taking that base, and it's literally base times height, right? And it's just that the base is pi r squared because it's a circle. And when we say height, we don't necessarily mean whatever direction is vertical, right? That you can have a sideways height. It's just a matter of, okay, you've got these circles, and then you're stacking all of them up. So you take the base of whatever that circle is, and then you stack up that many circles, however many corresponds to your height. So what we're going to be looking at with this method is, what if that height varies, right? So in other words, what if the side of your cylinder looks like this, right? And you've got something down here, and you've got something down here. Maybe you've got a flat on the bottom here, or not, right? Maybe you've got another curve that kind of matches it like this. What do you do if your radii are not all the same? And that's where calculus is going to come in. So here we have a curve, f of x. And the idea is, what would happen if you take this curve from 0 to a and revolve it around the x-axis? Okay, now there's a fun little animation here, but I'm also going to then just kind of draw a sketch based off of this. So let's look at the animation first, because it kind of helps us put this in perspective. It kind of forms a shape that looks like a base in this case. So this curve f of x, basically the idea, right, is that you're going to spin it around, right? It's like you take something flat like a Post-it and you spin it around a pen, for example, right? And the pen would represent the axis, and you've got a Post-it or some shape that you are spinning around it. And if we were doing this in person, I have a fun activity that goes with this, but obviously I can't do that online. Anyway, So you're taking something and you're spinning it around, right? So that this edge, what that does is it kind of becomes the outside, and it just spins around and kind of forms this three-dimensional shape, right? That as you're rotating it around, your radii of your cylinders are varying with the height of the curve, but that it forms this shape. I didn't draw it great, but you get the idea? So you're taking a 2D thing and you're rotating it to make it be a 3D thing. That's the basic idea with these. So how do we find the volume of that three-dimensional object? Okay, we are going to start with something a bit simpler than that curve we just looked at. We are going to look at the square root of x. And we're looking at the region that's going to be bounded by the square root of x and the x-axis, from where they intersect at x equals 0 up until x equals 4. Here. So it's going to be kind of like our starting point for this. And the idea is that we're going to be rotating this around the x-axis. Okay, so let's say that we've got this root x curve, and we're trying to design a cone for a rocket, right? So if you think about the nose of a rocket or an airplane, right, that it's kind of this curved shape, right? Just like the nose, like the end of it. So we put something in, let's say this is us saying we put a wood in a lathe, right? But the idea is that we're going to take something and we're going to rotate it to make it match kind of this curved shape of like a nose cone. Okay, so how do we find the volume of that, right? Let's say we're going to like 3D print it and we need to know how much material do we need to fill this in solid, right? This is going to form a solid figure. So how do we find the volume of that? Okay, so here's the idea. One idea is that we're going to put it into a series of thin slices, right? That every time I were to slice this cone, right, that every like slice of this would be a circle, right? Because we've rotated it, right? So that would be like the diameter of a circle, right? And we would have a circle at the end. Everything is circles in here, and those are all the diameters of different circles. So if we want to find the volume of each of those, there we go, there's my little circle animation, right? That you've got the radius up here, this right here is going to be the radius, and you rotate that around to make a circle, right? But you're rotating it around the x-axis, right? You're doing a little rotation here. Okay, so if we think of each of those as an infinitely thin cylinder, right? So basically they are circles, pi r squared, but with a minute little thickness or height to them. So if we say, well, each one of those is pi r squared h. Okay, so how do we determine what's the r squared and what's the h? Okay, well, pi is pi, right? That's no mystery. But r is going to be determined, like we said up here, that r is going to be determined by that curve, right? And that as you have values closer to 0, you're going to have smaller radii. But as you get closer to 4, they get larger, right? At 4, the radius would be 2 because the square root of x, the square root of 4 is 2, right? Square root of 1, at that moment, your radius is 1. And for all those values in between, it's just going to be root x for that value. So r, the radius, is coming from the output of the function. H, for each one of those, we said these are going to be infinitely thin, right? It's just like in the past when we talked about area and we were splitting it up into rectangles, and we said, well, the rectangles, the amount of rectangles is approaching infinity, so the thickness of the rectangles is approaching 0. Same thing here. The thickness of the cylinders is approaching 0 because we want to fit infinitely many of them under the curve. So that h is our differential dx, meaning a really small change in x, just like a delta x, right? Really small change in x. Okay, so every individual slice along the way is going to be one of those pi root x squared dx's. Okay, but we have a lot of them, right? We just said we have infinitely many of these. So if each one of these is pi root x squared dx, and we want to put all of them together, then we need the sum of all of these volumes from 0 to 4. And that's where the definite integral comes in, right? That the integral symbol is a long, skinny letter S because it stands for sum. So we integrate from 0 on the left to 4 on the right, and it's pi r squared h, but r is coming from the curve, and h is differential dx. Then we can solve. Okay, so there's a pi, there's a root x squared, so that's great because that just becomes x. That's simple. And then we just do the power rule to get the antiderivative, right? If I have x to the first, that becomes x squared over 2. And we just put the pi over 2 out in front. And then I plug in the 4. 4 squared is 16. Half of 16 is 8. And then that's minus 0. So the volume is 8 pi. So, to summarize and to generalize, right, that your idea, all this stuff comes back to the idea of the volume of a cylinder. So all of these are going to have pi in them. Pi r squared h, and r squared is coming from whatever your curve is, right, because that curve is going to be your radius, okay? So your top minus bottom, whatever that is from the graph, that is now your radius in this scenario. And h, all h is it's your dx or your dy. So the differential is the height because it's the very small, infinitely thin thickness of these cylinder discs, right? So they're discs. So that's why this is called the disc method. The idea is that you've got these really thin things and you're rotating them around like a CD, right? A compact disc. So you have all of these that you're just adding together. So in general, if you were rotating around a horizontal axis, that could mean the x-axis, but it also could mean any horizontal line. Today we're going to stick to the x-axis, but tomorrow we will look at other horizontal axes like the line y equals 1 or y equals -2. So in general, for any horizontal axis, you will be going with respect to x, and this will all be a dx scenario. Okay, pi r squared dx. And that r of x is here to say, like, okay, it's just whatever the function is, that's your radius. And then if we're rotating around a vertical axis, such as the y-axis, or x equals a constant, right? Like x equals 2 is a vertical line. For those, you're going to have to switch to be in terms of y. Okay, because if you are going the other direction, right, then your thickness of whatever it is that you are rotating, the thickness of that is going to be a really small change in y if you are rotating around a vertical axis. So just something to keep in mind. We will look at both, and we'll look today again just at the x-axis and the y-axis themselves, and tomorrow we'll expand to like x equals 2 and other constants. So just another kind of visual representation of this, because this is better than hand-drawn little sketches. Everything goes back to pi r squared h, right? So you have some function, f, whatever, that becomes your radius. So pi in the front, don't forget to square the radius, and then you've got dx or dy, depending on what type of axis you're revolving around, whether that is a horizontal axis or a vertical axis. Okay, so let's jump in with some regular examples. Okay, so this is a pretty typical way to see one of these problems, and these are really common FRQs, but let's see. Find the volume of the solid of revolution generated by revolving the region bounded by the graphs of y equals 2x squared, y equals 0, x equals 2 about the x-axis. Okay, the very first thing you always want to make note of with these problems is what is your axis that you will be revolving around, and is it horizontal or is it vertical? Because that will tell you if you need to be in terms of x or in terms of y. So this is a horizontal axis, right? The x-axis is a horizontal line. So that means that we're going to be doing everything in terms of x, which is good news, right? That's easy. It's just like with cross sections, right? If it says perpendicular to the x-axis, that means it's dx. Kind of the same thing here. If it's a horizontal axis, that means it's dx. So that's good. Okay, the next thing is you want to generate a sketch of your curve if it's not already been provided for you. So this is y equals 2x squared, y equals 0, and x equals 2. Okay, so here's my little hand-drawn sketch. So y equals 2x squared is just a little stretched out parabola. Y equals 0 is the x-axis. And x equals 2 is just a vertical line. So we can see, I've highlighted here, the region bounded by those three curves. And we are going to be revolving that around the x-axis to form a shape. Okay. So, our radius, just like when we've done area in the past, right, your radius in a dx scenario is going to just be top minus bottom. So the parabola is bounding this region on the top, and y equals 0 is bounding this region on the bottom. So that means that our radius function is going to be 2x squared minus 0, which is just 2x squared. So that's our radius r of x. And if we were to spin this around, it kind of forms this kind of funnel shape. A lot of these end up looking like funnels or kind of weird cones or vases sometimes, right? Like that other one in the animation earlier, it looks like a vase. This one looks like a funnel, but it's solid, right? It's forming a solid closed-in figure. And next week we actually will look at some that are hollow figures, right, that have an opening in them of some kind. But for now we're sticking to solids. Okay, so once you have your r of x and you have your bounds, so here our bounds are going to be, let me highlight in a different color. Switched off the highlighter. There we go. So we've got 0 over here on the left and 2 over here on the right. That's my left and my right. So those are going to be my bounds when I set up my integral. So when I set up my integral, pi r squared h. So here we go. The volume of the solid is going to be pi times the integral from left to right, so 0 to 2, of 2x squared squared. So it's very easy to forget that your r is squared. And it's also easy to forget the pi out in front. So just remember, right, pi, pi. Pi r squared h. Okay, so I've got my pi in the front of the integral, or you can put it inside, it doesn't matter, it's a constant. Take your radius and square it, and the dx is the h. Okay, now sometimes on these it will only ask you to set it up and not necessarily to solve. I'm going to go ahead and show the solution for all of this, but kind of like when we did cross sections, I'm more concerned with making sure you know how to set these up. Because solving it is just the definite integral techniques we've discussed in the past. But let's do it. So 2x squared squared, make sure you square both the coefficient and the variable, right? So it becomes 4x to the 4th. The 4 can move out in front with the pi. In the interest of time, I'm going to click through this pretty quickly, but it's all there that you can see. I do the power rule, right? Because 1/5 x to the 5th. 4 pi is just chilling out front. Plug in the 2, plug in the 0. 2 to the 5th is 32 times 4 pi over 5. And our volume comes out to be 128 pi over 5. So like I said before, pi is always there, right? Because of that pi r squared h. It's in these, like a bunch. Okay, so this one is pretty simple, right? One thing I do want to point out before we move any farther along is that y equals 0 here was the x-axis. So our axis that we were revolving around was also one of the sides of the figure, right? That this y equals 0 was both an axis and a boundary. Now, altogether with volumes of revolution, there are going to be two methods, disks and washers. Today we are focusing on disks, but one of the things that makes it a disk as opposed to a washer is the idea that if one of your boundaries is the axis of revolution, that makes it a disk. Okay? When there's a gap between your axis and the boundaries, that's going to be the washer method that we will talk about next week. So just something else to start looking for, right? Identify your axis at the beginning, like we said, so that you know if it's dx or dy, but also look at your boundaries, and if one of them matches the axis, then that tells you it's the disk method specifically. All right, so with that in mind, let's look at the next one. It looks almost like the same problem, but there are some differences. Find the volume of the solid of revolution generated by revolving the region bounded by the graphs of y equals 2x squared, y equals 2, and x equals 0 about the y-axis. Now the parabola is the same, but everything else has changed a little bit, starting with the axis. So this is now going to be a dy scenario because we are going to be revolving around a vertical line. We do still want to use these three curves to generate a sketch of what we are going to be revolving. Also, these two curves are different from the previous example. The previous example was y equals 0 and x equals 2. This is actually a different region because we have y equals 2 and x equals 0. So our region looks like this now. I have y equals 2x squared, and that's still the same thing. Y equals 2 is a horizontal line up there. And then we've got x equals 0, vertical line over to the side. But also, we're going to be revolving around a vertical line, the y-axis, which the y-axis, also known as x equals 0. Okay, so again, our axis that we're going to be revolving around is one of the boundaries of the figure. All right. So if we were to revolve this around the y-axis, it makes kind of this solid bowl shape, right? You can kind of see it there. If you're just revolving it around so that your radii are sideways now, right? So that means the thickness of each of those is a really infinitely small change in y, and they're varying as you go from 0 at the bottom to 2 at the top, right? That 0 and that 2, those y values are going to be where those radii start at the bottom at 0 and stop at the top at 2, right? So those are going to be your boundaries for your integral once we get to that. But also, we have this y equals 2x squared, and we need that to be in terms of y, because again, this is a dy scenario because of a vertical axis. So I'm going to take that 2x squared and I'm going to solve it for x. Divide both sides by the 2, take the square root. So our radius function in terms of y, the right is root 1/2 y and the left is 0. Right? Because it's just x equals 0 is our left boundary here. So keeping in mind that our bounds for y are going to be 0 to 2, bottom to top, and our right minus left is just that root 1/2 y minus 0, pi r squared h. So you can put pi out in front, because again, it's just a coefficient, so it can just chill out there and wait its turn. And then we've got the integral from 0 to 2, right, bottom to top. And then we take our radius and square it. It is so easy to forget that square. Just a little 2 up there, but it matters. So we've got our radius function, root 1/2 y, and then squared, and then dy. And again, sometimes setting it up is all they ask you to do, so that's nice. So we've got our bounds. We talked about that, bottom to top. Okay, so squaring, again, this time because it's a root function, comes out to be nice. It's simple. Okay, squaring out the root, pi. So that's pi over 2, and then just integral y dy. So if we do the power rule, I'm going to go through this kind of quickly, but you do the power rule, it goes up to the second power over 2, right? So we've got that pi over 4 in the front. You just put those 1/2 together. And then plug in the 2, plug in the 0, and it becomes pi over 4 times 4 minus 0. It's pi, just pi. So that's the volume of the solid. All right, one more. What is the volume of the solid generated by revolving the region bounded by the x-axis and the graph of y equals 4x minus x squared about the x-axis? Okay, so first of all, we're back to the x-axis, so that means it's going to be dx again. Good news. Also, our two curves are the x-axis itself, which tells us this is a disk because it matches our axis of revolution. And this parabola, this is an upside down parabola. Okay, so you want to have a sketch for several reasons. It helps you identify your radius and it helps you identify your boundaries. So 4x minus x squared is an upside down parabola that's been shifted a bit to the right. Right, it's just like negative x squared plus 4x. Okay, so that sketch looks like this. Now, I already have the 0 and the 4 labeled, spoilers. But if they were to give you this on an AP exam for you, the 0 and the 4 would not actually be there. But we need to find our points of intersection. To do that algebraically, considering that the x-axis is just y equals 0, you just take those two curves, the y equals 0 and the y equals 4x minus x squared, and you set them equal to one another. And you just solve for x, right? Just like when we're doing area or cross sections or any of the related topics here, if you need to find the points of intersection, set the two things equal and solve. Now with the 4x minus x squared, I can factor out a common factor of x, right? So that's just x times 4 minus x. And then my solutions are 0 and 4. So those are the boundaries. That's where those two curves intersect. And my radius is going to be top minus bottom, which is 4x minus x squared minus 0. Again, tomorrow we'll look at ones where the bottom function, quote unquote, is not 0. So stay tuned. All right, then we just have to set up our volume integral. So pi r squared h. Pi r squared h. So pi integral from 0 to 4 r squared h dx. And I have it on the slide all written out, all the steps. Again, this is one, and this is a multiple choice, right? So womp womp, you would have to go through and figure it out. So just to quickly go through that to not take up too much more of your time, you would have to FOIL that out. We can't use sub that as it's currently written, but you can FOIL things. That's still a thing. I just rewrote it and put it in order. Then I did the antiderivative. Pi is just waiting out in front, just chilling, waiting its turn. Then you would plug in the 4, and then you would be really grateful that the bottom limit is 0 because it's all that stuff just minus 0. So that's nice. And eventually, a whole lot of arithmetic later, eventually you get to D. It's 512 pi over 15. If there were something like this on a multiple choice, you could just figure out which one is equivalent to that on a calculator or something. But anyway, that is it. Thank you for watching, and have a good one. Stay well.